Well, the old homemade tractor finally needs a little bit of service. So I built this tractor about 15 years ago, and I really haven't had to do much to it over the years. It's all hydraulic and hydrostatic. So what's happening here is that the starter solenoid is welding in an on position, which, as you can imagine, is really not so great for the starter motor. Unfortunately, it is buried inside of this thing, so we're going to have to do some major disassembly to get this thing apart. So, got to take the gas tank off, the instrument panel, the steering wheel, the seat, the tray on the back, and then the body can come off. So, then you'll get to see what is inside of my homemade tractor. Hang on. Well, we got her apart. And there's the offending solenoid right there. But you can see how this thing works now. There's a big hydraulic tank. And then over on this side, this is the pickup. Inside of this tank, there's a siphon tube down to the bottom with a magnet in it. So it comes in here, it goes through a filter, then it goes to a hydraulic pump, and the pump is driven off a shaft. And I can't see this display. I hope you guys can see this. Okay, there's a coupling, and then it goes down through the floor and hooks to a double row pulley that goes to the motor. Okay, then out of the pump it goes to my valve body, and then, you know, to the various places. I have all my attachments are hydraulic, and they drive off this quick connect. And I have a lift cylinder in the front for the plow part of it. But there it is, man, in all its glory. A homemade tractor. The whole frame is made out of 1/4-inch wall tube steel. It's got a hydrostatic transmission in it. It's driven off another belt off of the pump pulley. So we'll clean the crud out of it and take a look at the solenoid and see what's up with that. Alright, we got a little post-mortem going on here. Got the solenoid out, and it's a little screwed up. That could be fixed. The problem is this little ground thing here. This is what's making it intermittent. I don't know what's causing it to remain locked on, unless it's just, you know, a tired spring or something, but I think we need a new one of these things. So that's the scoop. I think we're going to head off to the auto parts store and buy a new one. Well, 21 bucks later and a nice bike ride. We have our new solenoid in there. So now we got to start putting this thing back together. But I just want to give you a final look-see. The guts of this thing before I put it back together. So that's what's involved if you want to make your homemade tractor. Well, I got her back together. Let's see if I can show you how this works. So there's a double belt pulley on the engine. There's a triple on the jack shaft. And there's one going back to the hydrostatic transmission. And it's an open center system, which means that the pump's always running, the oil's always flowing, and it only builds up pressure when you put a load on it. It's the easiest kind of a hydraulic system to build, but it's less efficient than a closed center. And a closed center uses a variable displacement pump, and it builds pressure immediately, but there's no flow until there's a drop in the pressure. This damn hornet looking for something to... Don't you be building no nest in my tractor. Go find a flower. So anyway, where was I? Okay, yeah, so closed center system, there's no flow until one of the valves is opened, and the pump will servo to maintain pressure for the different flow conditions. It requires a much more expensive variable displacement pump, a piloted pump, but it's more efficient because there's no flow when there's no demand. So anyway, that's the scoop. Let's see if this bad boy will start. I don't hear the starters running, so that's a good thing. Alright. We'll keep her running for another 10 and 15 years. Back in business. Alright. I'm going to try a little beginner hydraulics here. There's two main types of hydraulic systems. Open center and closed center. And primarily that is the pump and the valves that you have. My tractor is an open center system because constant displacement pumps are cheaper than variable displacement pumps. For example, a constant displacement pump would be like a gerotor pump or a vane pump. Something like that. A variable displacement pump is something like a piston pump with a swash plate so that you can control the stroke of the piston. And those are real expensive. Sometimes you can find them as surplus parts for, you know, some short money, but as a general rule, constant displacement pumps are much cheaper. So the disadvantages of an open center system are that there's a constant loss because the pump is constantly running, and so there's flow going through the tank, through the filter, through the pump, through the valves continuously at a very low pressure, basically like, you know, the friction of the whole system is what's causing a slight amount of pressure at the outlet of the pump. When you activate the valve for, say, a cylinder, what happens is it diverts that flow into the work, which creates a restriction or resistance to the flow, and that causes pressure to build up in this leg and do the work, and then it, you know, flows back through the valve body and returns to the tank. So there's, you know, a disadvantage there of, you know, you're constantly dealing with flow in the system, and that does, you know, take up, you know, horsepower in the form of heat. So the difference of a closed center system is the pump has a servo port on it. So when you start this up and start turning this pump, pressure will build immediately into this line and feed back here until it reaches a set pressure in this loop, and then statically it'll just stay there, because this is a dead end in a closed center valve. In an open center valve, this is just, you know, flowing through the valve body and returning out the return port. In this situation, this is closed, and all these work ports are closed, so this is a pressure line into the valve body, and there is no flow through the valve body and into the return line. Now when you open a work port here and oil is allowed to flow and do work, there's a pressure drop here. The pump will sense that through this feedback line and increase its displacement to maintain that set pressure. So you don't have this constant flow situation that's just burning up horsepower when you're not doing a lot of work. Now these are very simplistic diagrams. I've left out things like safety valves and drain returns, things like that, just for the sake of simplicity here. Another big disadvantage of an open center system is that inside of the valve body here, if you want to just power one work element like a cylinder or a motor or something like that, then you know the oil flows in here and flows out here and goes back to the tank. But if you want to power two at the same time, like for example on my tractor, when I have the snowblower on there, I have a lift cylinder and I have a motor that's spinning the auger. And what happens is that the oil will flow into this thing, flow out here, flow in here, flow out here, and basically these two devices are in series. So they share the power. Over here, each of these is a dead end. So when you open a work port, the pressure will still be constant, but the flow will be into each of these things simultaneously, and they will return simultaneously to the tank. So these are essentially in parallel. And what the effect is over here on my snowblower, when I activate the lift cylinder, the oil is starved from the motor so that it will, you know, lose power. If I had a closed center system on that, that wouldn't happen, because the pump would compensate for the drop in pressure and increase the flow. So it's a little better thing. It's, you know, most of the consumer stuff you see on the market that has hydraulics is an open center system. Most of the big stuff you see, like construction equipment and big tractors and stuff, that's closed center. Okay, so there's another variant of the open center system, and it's sort of like designed to compensate for the problem of these things being in series and stealing power each other, and it's called power beyond. And normally in a non-power beyond open center system, the valves have two cores in them, which means it switches the power port and the return port, one for each core. So like the first core would take and connect the intake of the valve core, of the valve body, and route it through the first core in the valve to the load. And then the return line on that device would go to the second core in the valve, and that would route it to the return line to the tank, so you get the flow through the valve. A power beyond has a third core in it, and what that does is it will feed high pressure oil to the next port. So it essentially puts these in parallel as well, at the expense of an extra core in the valve. Now, there are other ways that you can use a constant displacement pump in a closed center system, but it requires an unloader valve on the pump, which basically short circuits it. So you still get the pump flowing here, but it doesn't flow through the whole system. Okay, so I got some crappy artwork here, but hopefully you'll be able to understand it. Maybe you've seen these things before, but for constant displacement pumps, there's a gear rotor pump, there's a vane pump, and there's a gear pump. There may be more, but those are the ones that I know about. And you can't change anything. Basically, flow is proportional to the RPM. You know, depending on the displacement of the given pump, then, you know, it's RPM times displacement equals the flow. Okay, now we get to the piston pump. These are variable displacement pumps. And like I say, there may be different kinds, but this is the kind that I know about. So what basically happens here is, this is a swash plate, and these are ball bearings that ride on that swash plate, and they can push on pistons that are connected up like little pumps. And I've drawn two here, but usually there's like 6 or 8 rotating around like in a cage type structure. The swash plate is stationary, at least in the pumps that I've seen, and the swash plate, the piston assembly rotates around with the shaft. So in a position like this, the pistons aren't pumping because they're just, rotating around in that plane, and there's no movement back and forth of the pistons. But this swash plate can tilt, and when it does, now when the piston rides around, when the bearing rides around the swash plate, it pushes in and pushes out. And so that's how they control the displacement of a piston pump. Now, the swash plate can be controlled by a couple of things. On a hydrostatic pump, which is, the basic form of this, and it would be used like in a hydrostatic transmission where you would connect wheel motors up to it. This would be controlled by a lever. And what's really cool about it is if you tilt it this way, it's forcing fluid in one direction. But if you tilt it this way, it's forcing fluid in the other direction. So you get bidirectional flow with this type of pump. Now, in the closed center system here, this swash plate is controlled by a piston, which is connected up to a spring. And that tension on that spring sets the pressure that the pump will produce. So it's a differential type system. One side of that piston is connected to the output of this, and the other side of that piston is pushed on by the spring, and it can move this swash plate. And typically in a system like that, it's unidirectional. It doesn't go both ways, it just goes one way. So I was digging through some stuff for this video, and I came across the build book for my tractor. Here's some of the calculations you have to go through, like calculating out how many gallons per minute the pump will deliver at a given RPM. The displacement on this particular pump is 1/2 cubic inch per rev. So, you want to calculate how fast your auger wants to spin, or the load, and what the pump RPM is going to be, and if you figure out the horsepower required to do that job, and you come out with 13.6, which I have a 20 horsepower engine on that tractor, so I got plenty of power to do it. For the motor, you want to have, this is a design number. I'm trying to remember now. This number here I picked based on what I want the auger to spin at. And then my motor displacement is 0.6 of a cubic inch per rev. So at 4,000 RPM, it would take 10.8 gallons a minute. At 26 RPM, you extrapolate, you get 7 gallons a minute. So the pump can deliver that up here at 3,200 RPM. It's delivering 7 gallons a minute. So this design worked. Let's see. When you run the calculations backwards, you come out with a required horsepower to spin that auger of 12.2 horsepower. So I have a 20 horse engine, and that's, you got to factor in a derating factor for that as well. But that means that I can deliver 12.2 horsepower of that 20 to the auger. Now keep in mind, I also have the hydrostatic transmission to deal with, and there is loss in the system as well. So, there's some, that's like a little more than half of what the capacity of the engine is. So those are the kinds of things you have to do. Here's my open center system design. And I have some parts that I've ordered online. Here's flow versus RPM for my motor. I haven't looked at this stuff in a long time. And then I've got the engine specifications for my particular engine. I've got the schematics for, what I wired up in there. Here's the hydrostatic transmission that I'm dealing with. That was the owner's manual, I believe. Yeah, this was like the spec sheet for it. Capacities, temperatures, displacements for different models, dimensions, this kind of thing. This is how I designed it into the tractor, and then fortunately I was able to get the repair manual for it too, because it came with these round shafts, and I had to make them D shafts. I had to mill like a double D, which is a flat on both sides of it, to fit my wheels. So I had to take this transmission apart, and that's what I needed the service manual for, so I could get it in the mill. Here's all the procedures for servicing it. Now, actually, here's a picture of a georotor. This is an open center type of transaxle, where it has two wheel motors and a pump in the middle, and it acts differentially. In other words, both the motors are in parallel, so if one sees more load, the other one will spin faster, and that's how you get the differential action for the steering. Yeah, here's how the wheel motors work. Okay, so the motors are rotor ball motors, which are a little different. than a gear rotor, but it works. And here's the old, when I bought this tractor originally, I got it off some guy. I was driving by his house and I saw it, and I bought it just so I could have the seat, the body, and the hood, and the deck. The rest of it I scrapped, and I just, built my own, to fit these parts. And that's how I came up with the dimensions of it. More engine stuff. Picture of the head gasket. It did blow the head gasket once, but it hasn't, I fixed it and hasn't done it again yet, so. Alright, so that's the scoop on that tractor and how it works. Hope I taught you something there with my limited knowledge of hydraulics, but I do have a couple of practical and working versions of these things. And I do have a tractor out in the other shop, which I will show you. I'll mention it as a teaser, but it's much bigger than my little tractor, and it has a 40 horsepower diesel engine on it, connected up to a hydrostatic pump and a closed center servo pump, and it has power steering, and it has a wheel motor on each wheel, and it has valving to control the fluid flow to each wheel. So it's four-wheel independent drive. I can't show it to you now because it's dark out, as you can see, and there's no power in that particular building. So one of these days on one of these doodads, you will see that. Have fun. Thanks for watching.